Hey everyone, I am Ankit Nishad from MATLAB Input and will be showing you all a fun with Simulink by modeling a spinning skater using MATLAB Simulink. Let's start.
Do you know what are spins in skating? Well, spins are an element in figure skating in which the skater rotates centered on a single point on the surface while holding one or more positions. Figure skating is undoubtedly one of the most aesthetically pleasing sports to watch. So, what can be the science behind these spinning skaters? Let's dig it out. The skater starts off in a standing position and spins about the vertical axis. After a few rotations, the skater pulls both arms in closer to the body and spins faster. In physics, we call this angular momentum. It can be called an illustration of angular momentum, where momentum is the product of angular velocity and moment of inertia. Since momentum remains constant, if velocity increases, then inertia decreases and vice versa happens. It is interesting to know that we can make a 3D model through MATLAB Simulink of spinning skater spinning through the body movements. Before starting the simulation, I would like to show you the spinning skater 3D model that we will be making in this video. This model has a body, a neck, two arms and two legs moving in clockwise direction. During the simulation, first the leg is made go down, accelerating the body a little. A few seconds later, both the arms go closer to the body, reducing the moment of inertia and accelerating the body more significantly. To make the model move and run like this, we will be using the SimMechanics in Simulink to make the model behave as we want. For this simulation, we need to know some basic concepts of SimMechanics used. The basics are global coordinate system, body coordinate system, rigid transform, and revolute joint. Global coordinate in Simulink is defined as such that the direction of the x, y, and z axis are oriented in such a way. The body coordinate system can be oriented in any way. Rigid transform helps in connecting two bodies of different coordinate systems. The revolute joint models a joint that has one rotational degree of freedom. The axis of rotation is aligned with the z-axis of the joint base frame.
So now I'll be telling you how revolute joint works because it is a bit complex understanding revolute joint and modeling it through the model. So as we know, revolute joint revolves or rotates around the z-axis. So if I see that let the z-axis is coming outwards from here and the revolute joint makes it rotate around the z-axis, so it will move like this around the z-axis. If I show it like this, it will move like this. So right now my revolute joint is fixed here and the z-axis is coming outwards here. Now if the revolute joint shifts in between of my arm, it will rotate like a needle of the clock, as you see, in a 360-degree angle, taking less space. Like if it is here, it will rotate just here. But if I keep the revolute joint point here, it will take more space and rotate its whole like this through the whole arm. So this is the really important thing in this model which we are going to make, because making the joints and putting the joints, fixing the points between two models, the joints, is really very hard, and we cannot make the model or legs move easily if the joints are incorrect. So this was the revolute joint. Now let's continue ahead.
Now, keeping the model in mind, let's start from the basic. Type SMNew in the MATLAB code editor. You will see a solver configuration on which the model simulates the world frame or the global coordinate axis, the mechanism configuration, a solid block, a rigid transform, a Simulink to PS converter. Take a revolute joint, a scope, a body, with 0.3 meter radius and 1 meter length, and a body with 0.1 meter radius and 1 meter length, and a neck of 0.15 radius and 0.3 meter length. Now take a revolute joint and connect it to the global coordinate system. Specify the velocity target minus 1200 degree per second on which the whole model will rotate, and click the velocity in the sensing to see a simultaneous model to graph representation. Connect the rigid transform. Take the method of Cartesian in translation mode and put the offset 0.5, where body's coordinates are defined at the end from middle for the leg rotation. Then a rigid transform of Cartesian method 0.5 and another Cartesian 0.2, 0.5 for the right leg to be attached in right corner of the area of the body. Now we need a left leg to move. So we need a rotation of leg around x-axis in 90 degrees. For it, the joint should be at the end. Take a left leg, attach a rigid transform of 0, minus 0.5 for the rotation from the end. And then take a rigid transform about x-axis in the positive 90 degrees. Connect a revolute joint. Put the torque automatically computed and motion provided by the input. Since we need the leg to go down at a particular time, then attach a rigid transform of plus x-axis of minus 90 degrees, then a rigid transform of 0.2, minus 0.5 from where the left leg will be attached in left corner. Take a step of 2 seconds and initial value minus 90 degrees and final value to 0 with a Simulink to PS converter. Now for the left arm, take a cylindrical body, a rigid transform of 0, minus 0.5 and rotation of plus x and angle 90 degree. Revolute joint with automatically computed torque with motion provided by input. Then a rigid transform of rotation around plus y-axis with minus 90 degrees. And rigid transform of 0.3, 0.5 and then a step signal with step time 6 with initial value 0 and final value. Run the simulation and the model will run something like this. So there is a mistake in this model, which either me or you can usually go through while modeling this model. We replaced here leg with the whole body. Now we can see a good result coming up here. Now, completing the model, connect the right arm with cylindrical solid of radii 0.1, a rigid transform of 0, minus 0.5, a rigid transform of rotation around plus x-axis and angle 90 degree, a revolute joint with same configuration of previous, a standard axis around minus y-axis with angle minus 90 degree, and a rigid transform with translation of 0, minus 0.3, 0.5 connecting the body. For the neck, take a Cartesian of 0.65 and connecting to the solid of 0.15 radii and 0.3 length. Then take a scope of 6-second step time, initial value 180 degrees and final value 270 degrees step. Now compute the model and run the simulation on fixed step and size of 1e-5 and solver ODE3 Bokagai Champagne. Periodic sample constraint unconstrained allow tasks to execute on currently on target. Time period of 10 seconds. You can see the body accelerating with the body parts moving closer to the body. You can also change the speed of the hole by changing the velocity through the revolute joint attached to the world frame. And you can change the time when the body joins through the step times and how much degree you want to move or in which direction. So now you can also win Olympic medal by increasing your speed with right physics and right posture and shine bright through MATLAB Simulink. So this was this fun with Simulink from my side. Thank you for watching this video. Do like this video if you found it helpful. If you have any queries, post them in the comments. Follow us on LinkedIn, Facebook and subscribe to our YouTube channel. Education is our future. MATLAB is our future. Happy MATLABing!